Okay, can you hear me? Okay, super. So, hello on my talk. I hope you get your coffee. And today we will be talking about living in eventually consistent reality. And maybe a little note before I start the talk is that first part might be a little bit theoretical. We get to the more practical examples in the second part of the talk. And since there is a lot of material I've got on those slides, we might run out of time before I will present them all. So just in the case, this talk will be published online, and all of the code is prepared in the way that you can use it as a tutorial and play by yourself. So I am Bartosz Sypytkowski, and here are all of the contact informations if you want to reach me afterwards. What we will be talking about. We will be talking about how do you synchronize and replicate data over the web in context of various databases and libraries that allow us to do it in a way that it's resistant to network failures, network delays, using data structures known as CRDTs. We'll see what existing databases could we use in this context and how they look inside. I mean, we are going to do a deep dive in a way that will allow us to build some of those things by ourselves, simply because it's not exactly possible to fix all of those issues that we might have on the production using only existing code, like gluing the code of the APIs of existing libraries and frameworks. Sometimes we need to be able to build something by our own, which is also very nice. And we also, if time will suffice, we'll talk about different notions of time and how can we represent time in different ways than using standard wall clock times. So let's say we have somewhat practical example. We will try to build a YouTube 2.0. We'll face two features that we would like to have. One of them is what we could do for YouTube is video streaming. So let's say that we have Alice. She lives here in Oslo. She wants to publish some kind of video. She publishes it to the closest server, in this case probably somewhere in Ireland or something like that. And her video was very popular, so popular that it was reached by people all over the world. If this video would be all served from only one single data center, it could probably cause some issues, simply because of the amount of users that we would like to have. Because when the server fails, we might have a problem because users don't get the video when they want to. So the simplest solution for that is to replicate that video over several different data centers, probably living on different continents to reduce latencies, to make our solution more resilient. And this is simple for something like video upload because it allows us to, it's based on the concept of single writer, in this case Alice, and multiple readers. We know how to do those things. We can even build something on top of that, like replication protocols like Raft, Paxos, and so on. However, let's say that we would like to have another feature, something like video counter. It's also a very popular one. However, the thing is changing here a little bit. We have shift from a single writer to multiple writers, because every single person that seen that video is basically trying to update this single counter, and this is in theory we can think of it as a single value that we'd like to increment. Now, if we would like to coordinate and synchronize the value of that counter as a single number, it could be a little bit difficult to do it without introducing any kind of latencies, conflicts. We would like to be able to do that on the multi-master replication system, something where we have no single writers but multiple ones. And this creates a question, can we synchronize data safely without the need for consensus? Because in this case, when we want to increment, for example, its counter value, the synchronization cost might be so high with such a large volume of updates that we want to process that we would eventually reach into some kind of hard limits when we would end up with only single writer in that case. And this is also when the CRDTs comes to work. We will describe exactly how to implement counter like that, and we could extend this solution for something like, for example, Azure or CosmosDB. So there is a theoretical map of how the CRDTs are built, because there are many kinds of them. We'll cover mostly the state-based version, but just if you are interested, you should know that there are also operation-based, which work slightly differently. The major shift here is that the more state-based is our data structure, the more complex it is. But at the same time, the protocol it is using for the replication process, it uses. In case if we are going through operation-based replication, in this case, the replication protocol is more complex. The advantage of having a lot of simple data structures. And if it's so, then why I am talking about state-based replication? Because building network protocols is a hell of a job. It's hard to debug, hard to implement. There's a lot of edge cases, and even complicated data structures are still much simpler than building a complicated replication protocol. And we can build them by ourselves and reuse the existing connections. Some of those things I will be talking about could even work over the UDP. So we could just, send messages and don't even care about if we get the response back or not. So what other use cases could we have for this kind of data structures? Any kind of replication where we can reach possibly long latencies. If some of you will in the future build a distributed system that is not only geo-replicated but something like solar replicated over multiple planets, then you will reach latencies in minutes or hours. And in this case, these are also data structures that will help you. So it's very long, long forward way of thinking. Also, any kind of synchronization that must tolerate periodical and disconnected devices. So this is also related to the first point, because if we have network delay in case of for example, 2 minutes, we don't really know if the device we are connected to is just, lagging in response or it's simply disconnected. And this is the case of distributed systems. Another thing is navigation. This is actual practical example from the company called NavCloud, if I'm right, because they built their navigation system on top of CRDTs. Chat applications. So any kind of application that have multiple simultaneous writers. Collaborative text editing, which is, to be honest, an interesting topic on its own. But two most common ways to solve collaborative text editors are operational transformations like Google Docs, and also CRDTs can be used in this context for peer-to-peer connections. Mobile advertising. Maybe you know a company called Rovio, the producers of Angry Birds. They've implemented a CRDT counter for their advertisement platform when they are using them to count the number of impressions the advertisers made on users, even if they are offline. And any kind of edge computing, so any kind of not client server, even in distributed mode, but just peer-to-peer connections when, for example, people are connected using Bluetooth devices. All of these are great use cases for CRDTs. And we have some existing solutions in that area already. Most common and most known, I think, is Riak. Have anyone here used Riak in the past? Okay. Riak is a key value database, and for example, it's used in British NHS. I think they are the biggest users of that. Another very big user is Riot Games, authors of League of Legends. And for example, their chat service is implemented in Riak. Another popular database, maybe not so popular, it's actually pretty fresh. It's NDC, which is also implemented just like Riak. It's implemented in Erlang. And what it allows you to do is to build a distributed transactions that are scaling almost in a linear fashion to the number of servers that you are adding to your system, which is actually a great feature to have. This way you can have like 500,000 of transactions per second if you want, just adding enough servers to handle that case using CRDTs. A very common case is Amazon DynamoDB. So if you are using AWS, you have also this key value store in your reach. Lately, they also added support for transactions, multi-key transactions for that. Azure CosmosDB is not using CRDTs by itself, but it has something that is called multi-master replication. And when you configure CosmosDB to such case, you can write something that is called a stored procedure. It's using JavaScript as a language of their choice, where you can build your own conflict resolution logic. And for example, the thing I will be talking here about is implemented in JavaScript mostly because most developers already know JavaScript, and because you can use this piece of code as it is directly on the CosmosDB if you want. So while CosmosDB is not exactly implementing CRDTs by itself, you can use it to implement one for your needs. Redis Enterprise Edition also provided something that they called CRDBs, which is basically a CRDT on top of Redis. LASP is popular Erlang library that is pushing our knowledge forward that direction. Akka distributed data is a library or distributed actor framework built on JVM and .NET that you can use if you don't want to use a separate piece of infrastructure for a database to solve only a subset of problems, but instead you can use a library for that. Eventuate is another library also built on top of Akka, but only on JVM so far, that is using operation-based variant of CRDTs. Roshi is the library written in Go on top of Redis that was used by SoundCloud to handle their feature of following and unfollowing and subscribing to other authors and music creators. And AutoMerge is a JavaScript library that you can use for your, for example, JavaScript applications running on mobile phones, on desktops, and so on, to coordinate states with each other using something document model that is very similar to JSON. Sorry. So a quick intro to why and how CRDTs works. For example, using the previous case of single master multiple follower replication, we have a cluster of database clustered on several nodes. They are organized in leader-follower way, so usually there is one leader and multiple followers. When you want to read some data, you can read it from basically any node you want. However, when you want to write it, those followers need to first communicate with the leader and establish some consensus on what the correct order of operations should be presented by the users outside. This is a kind of contention point because we all depend on the leader. And given the network latencies in geo-distributed systems, and this can be a problem because, for example, sending a message from, for example, Dublin to Tokyo, it takes almost 300 milliseconds. This means that for this single entry, you would have at most 3 operations per second, right? If we will fit our message and our conflict resolution protocol in one round trip, which is not always the case. And this is based on the variant, on the assumption that we are modeling our protocols based on the world we know as humans. So we have leaders, we have consensus algorithms, we are trying to establish some kind of quorum because everyone have their different point of view, their different way of seeing the world. However, in masterless replications, there is no leaders or followers. Everyone are equal. Hey, socialism. So everyone can write to any node, and everyone can read. Everyone can read from any node, and everyone can write to every node. And nodes can just send the updates from themselves. And this is possible because we don't need to establish consensus if every replica can individually on itself build conclusion, the same conclusion as every other replica. This is a kind of Star Trek Borg collective way of thinking. Great way to build dystopian society, but it turns out that it works very well in distributed systems. So in order to reach that kind of convergence, how it's possible? So let's imagine that we have a local replica as a server. We are receiving requests for updating that replica into a different state. So we are updating it, serializing it, pushing over the network to another node. That other node receives an updated state, and it some kind needs to compare two of those states, the one that it received from a remote replica and one it has locally on its own, and resolve any kind of conflicts that could possibly happen in this situation. And this is done in CRDTs by something that is called merge function, just like merge in Git. But unlike Git, it doesn't need human interaction to solve the conflicting diffs. And in order to do so, it needs to achieve several properties. One of them is commutativity. So the order in which we are receiving those operations shouldn't even matter. Associativity is basically for the same reason. And idempotency is great if we want to build a distributed systems in general, because, for example, we could send those replication updates just in the loop for every 1 minute. It's not the very performant way of building applications, but we could do that. We could also push updated states through message queue or something like that, and don't bother if we receive that message one or more times. If we will receive it, we'll be able to handle it. And it turns out that we can use math to solve those problems, because the simplest math operations can actually be composed to solve real production problems using those properties. But what mathematical operations have those properties? Those number additions satisfy all of three? No, because maybe it's commutative and associative, but it's not idempotent. If you add 1 to 1, we don't have 1 in the result, we have 2. However, it turns out that there are 2 operations that we could use for that. One of them, very known, is mathematical maximum of 2 numbers. And another one is union of 2 sets. And we can compose those together to achieve some results. So going back to our distributed view counter. This is solved by something that is called gcounter. Please do not focus on this JavaScript, seriously. You can read it later on. What we can see here is that this is something that's called growing only counter. It means that this value can only grow upwards. And how it's implemented? It's basically a simple key value map when key is the unique identifier of our replica. It can be, for example, service instance ID in AWS, or if you have device, it can be a unique identifier of that device. And what we are basically doing is instead of having one global value that is describing our counter, we have multiple partial values describing increments done by each of the replicas. And each replica can only increment its own local counter, not counters of other replicas. So it looks like this. When we want to get the value, the total value of our counter, we just sum the values of all entries to get the total value. And this is presented here in this value function. However, now if we would like to merge those 2 counters, how can we do that? It turns out that all we need to do is to just squash the corresponding entries. And if the value components of those entries are differing from each other, we just take a max of those two. Why? Because this counter can only grow up, which means that the value that is higher is always more up-to-date than the one that we have on the place. So by taking the max of those two, we have the most up-to-date version of the counter. And this works in every direction. And it's very easy to achieve. So you can see that here we have, I think it's less than 20 lines of code. And you could use this already, for example, in CosmosDB using those multi-master configuration as a stored procedure to resolving conflicts. Another use case. So this counter can only grow up, but let's say that we want to implement something like a like counter or subscription counter. We would like to be able not only to like or subscribe, but also to unlike and unsubscribe. For this, we need to be able to decrease the counter value. However, we couldn't do that using g-counters for a simple reason, because if we would lower the value of our counter, there would be no way to decide if it's most up-to-date or not, because we are always taking the max of 2. But we could compose 2 counters together. And this is something that is called positive-negative counter, which is built of 2 counters. One which is counting increments and one which is counting decrements. So if we want to increment the counter value, we are incrementing the increment g counter. If we want to decrement the value, we take the decrement g counter and increment it as well. If you want to get the total value that we have, we get the counter value for increments, counter value for decrements, and just subtract them. And this way you can implement something that is able to both grow upside and downside. Another thing, let's say that we have voting system, but it's also, for example, a list of active subscribers. So we would like to see if a person who voted for some kind of survey, for example, is able to vote for it again, because we would like to save ourselves from doing voting on double hands, right? We shouldn't probably be able to unvote the vote that we made previously, because this would mean that the system that is handling this unvote option, that unvote feature, knows what was our vote, and this probably would cause some trust issues in our system, right? So we can say that there is no unvote option, but therefore we can figure out that the set of users who have participated in that voting can only grow up, just like our counter. But this time it's only a set. So just like we have g-counter, right now we have g-set, which is a growing only set. It's just ordinary set that is limited only to add operation and to merge. And merge in this case is simply union of 2 sets. I've implemented this set also as a plain JavaScript object, which can be serialized and deserialized. With that case, that special case, that here we are only interested in key component of the key value power entry, not in the value itself. Later on, we will use this value to other kind of stuff. So next thing, it's a distributed shopping cart, and this is something that was one of the, I think, first production CRDTs that was published by Amazon in their shopping cart option. So let's think that we would like to have built a shopping list. So we are sitting in the kitchen with our laptop. We are adding some things that we want to buy, like 1 banana, 2 bananas, 1 kilogram of strawberries or something like that. But later on, we would like to check out what we have in our garage or in our basement. So we are taking our mobile phone, we are going back to basement, and we lost the connection with the internet. But we still would like to be able to work over this shopping list, while, for example, our wife is still using our laptop on the first floor and also adding or removing elements from it. And when we are back from the basement, we'd like our application to synchronize those two different shopping carts together into one that has some sense, I would say, and not cause any kind of problems for them. And again, this is something that, just like we have a growing colony set, this is a growing colony map. It works in the same way that our growing colony set works, but in this case, the value component that we ignored in our gset is now a PN counter itself, positive negative counter. So we can add more values to our shopping list, or remove them if you want. And this is also a motivation if you are not yet decided why it's worth learning something like that. Because there's a very little probability that if you would have a case like that, that you will have a framework that will handle it for you this way. Usually, it doesn't happen this way. Usually, most of the frameworks give you only very primitive value types, and you need to be able to compose them together or introduce some technical debt because you didn't know how to solve it that way, so we solve it, some way around. But if you understand, if you have this kind of intuition, how to build those structures, then you can build something like this by yourselves. And this is probably something like 60 lines of code, including the PN counter implementation. So we simply can add more elements by using the entry as a key. For example, our banana would be an item, so the key of our key value map. And the value is PN counter itself, which is incremented or decremented as we want. Here the value, when we are producing the value, so for example, the result would be banana 3, strawberry 5, and so on and so on. We could also implement removing elements from it simply by not including 0 entries in our result set. It's very simple. And the merge operation works very simple as well. Basically, we are, again, squashing all the entries. And if there were different PN counters on both sides, we merge them because we know how to merge PN counters. So if there are conflicts, we use this merge operation to resolve those conflicts. And this is the power of composition when using CRDTs. Another case, let's say that we are implementing a kind of Twitter and we'd like to have a list of followers. So we would like to follow some user, unfollow it, follow it again, things like that. So could we do that using gset? No, because gset has only semantic for adding elements, not removing them. And we couldn't safely remove the values because if we then try to merge with another replica that didn't notice that this value was removed, it would reappear magically after resolving the conflicts. So if we composed two G counters together to build a counter that can grow and decrease its value, could we do the same with two growing colony sets? Yeah, in theory we could. This was already done. It's called two-phase set. So we basically have two kind of sets. One set counting elements added to that set, and one set counting elements removed from that set. And our result is basically a except operation from those two. So elements existing in add set that doesn't exist in the remove set. And we can do merge operations very simply just by merging the fields having those two G sets. However, this introduces a kind of problem because once we insert and remove element, we cannot insert it again. Because if we added element, we added it to add set, we removed element, we added it to remove set, then we add it again, adding it to add set. When we want to get the final value, the algorithm was take all elements from add set that doesn't exist in the remove set. but we have no options to remove to add again once removed element from that. And also it requires the tombstones. So remove set is also called tombstones from time to time. Sorry for that. So when we have those tombstones, we need to keep them alive forever. And this is a problem. And if I'm right, SoundCloud have initial implementation of that. And the issue in their case was that, for example, the list of followers, the active set that was presented to the user was a JSON of 5 kilobytes in size, while tombstones could reach even 2 megs. So it's pretty big bloat for something that simple. And this, of course, have been solved. So we are again having those 2G sets enhanced to have their value. The keys are elements, but the value are timestamps. Here, the timestamp is T1 for value A and T2 for value B. Now imagine that we have operations where we want to insert next element C in time T3. We simply add it to our add set. If we want to remove it at later time, we add it to remove set. We can actually move it to the remove set because it's not important if that value is in add set or remove set. It just needs to be in the composition of those two, so we don't forget about it. And we update the timestamp in which it was added to the remove set, so when it was removed. If we want to insert it again, we again can move it from remove set to add set, updating the timestamp. And this is something that is called right-wins set, and this is something that was implemented actually in SoundCloud to build their followers list. They were using timestamps in form of simple date time. So this was very easy for them to do. And the final value we are interested in this case is all of the values from add set with the timestamps that are equal or greater than timestamps from the remove set. So the items that we have added after we have removed them. Or if they were never removed, just we take them as they are. And merging, since we know how to merge numbers using the matmax operation, we also can use the same operation on timestamps as well. Now, this is a great solutions for, and this was the great solutions for solution for them, because usually we don't add and remove the same follower very often, but sometimes we might reach into cases when there is an OR set, so observed remove set, in which a single entry is added and removed multiple times by multiple users on different continents. And this is a problem when we are using wall clock timestamps, simply because clocks needs to be in sync. And this is something that is not really easy to achieve. Google Cloud created the entire infrastructure to build something they are calling true time, to implement a very, very precise notion of absolute time that is spanning the entire planet. They are using this with atomic clocks and GPS, and they still don't have a precision notion of time. True time is not a single point in time, it's a range from 2, which is representing that time. So it's not very easy to keep your clocks in sync. And another thing that we don't know about is whenever 2 updates that resulted in a conflict knew about each other. So sometimes we would like to know if 2 updates were conflicting in order to make some resolution algorithm for that, like merge operation if our values are CRDTs by themselves. And this is something that is solvable using vector clocks. Who are familiar with vector clocks? Okay, so vector clocks are basically a different way of thinking about time. We don't think about time in terms of physical wall clock time. Instead, we are using a logical notion of time. And And how do they look? They are simply key value maps, with key being replica ID, value being just a number, just like gcounter we introduced initially. However, when we want to compare the order of them, we don't use vector clocks for operations like get me all of the entries that happened after 10th of July, right? We use them to establish the relationships of happened before between each other. And they introduce something that is called partial ordering. So in standard ordering, when we compare two things, we have three states, right? Less, equal, or greater than. Here we will have four, and I will cover them in short. So two vector clocks are equal when all of their corresponding entries have equal values. If at least one of the values on the left is greater than the corresponding value of the right on the right, then we consider that vector clock to be greater than. The reverse case also applies for less than. And when we have mixed case of greater and lesser than values, we call these states concurrent in case of partial ordering for vector clocks. And this means that, for example, in this case, replica A updated a value and replica B updated the value, but they didn't know about each other updates. So we know that they updated the value in maybe not in exactly the same time, but before they got the updated replica from the other side. And in this case, we could, provide some kind of arbitrary decision how to solve this problem. This is just a piece of code. I will not explain what it does because I did it just a second before. I'm presenting it here for you in case if you would like to later on go back to this presentation and use it as a tutorial, because all of this code is self-contained. So if you will write it down on your Java, on your editor and run, it should run okay. So you can implement it straight from those slides. And this is a lot of code. Do not focus on it. We will focus on particular parts. When we are adding and removing elements from our set, we are basically incrementing the corresponding value of the clock for each of the sides. Just like we were using new date or in .NET new date time to get the timestamp, here we don't get the timestamp based on the system clock. We are incrementing the one that is already there, or we are using the empty one and incrementing instead. When we want to provide our users the result, we are comparing all of the entries from the timestamps, just like we did with date timestamps. But in this case, we want to cover all four states. So in case if our added insert timestamp was greater than or concurrent to remove timestamp, then we want to keep that value in the result set. If it was lesser than, then we don't want to keep it, and this is the case here. And if they are equal, then we should throw an error, because we shouldn't be able to add and remove the same value using the same timestamp. But I didn't cover it here, just to keep the code inside the slide. Sorry. So merging, just like we used matmax for merging timestamps based on wall clock, here we are using vector clock merge, which is the same as gcounter merge. Oh, and this is called add-wins observed remove set. It's a long name because we are favorizing adds instead of removes. So in case of conflicting vector clocks, when we have concurrent updates, we want to keep the value that was added, not removed. And this causes a problem. How much time do I have? Okay. How? Wow. Don't worry. I just don't want to, go through this too quickly because it's not an easy topic. And I'm afraid that some of you might get lost already, and there are harder topics ahead of us. So the problem with vector clocks and CRDTs in general is their space complexity, so the amount of memory or payload they are using because of all of that metadata that we want to keep around in order to resolve conflicts. So when we are using wall clock timestamps, usually they can be represented using longs, so 8 bytes per each entry. When we are using vector clocks, they don't have a fixed size. The size depends mostly on the number of nodes, so number of replicas that we have. Also on the key size of our replica. And here's the simple calculations that shows you how much more expensive in memory size or disk size is to have a vector clock. And this is, of course, the very optimistic calculation because it doesn't count the data structure, only the payload that is keeping this vector clock. We will come back to it later, I hope, because we have 20 more minutes. But yeah, something that could be used to make your own CRDTs much better is using deltas. Why? For example, imagine that we have built this follower list based on the observe remove set. Now we have somebody like Elon Musk. He has probably 11, maybe more millions of followers. We want to follow as well. So we click the follow link. We updated the OR counter, OR set, for Elon Musk on the local replica, and now we want to propagate this update to other replicas as well. So we are now in phase of serializing the 11 million of entries just for every single follow click. This is kind of pain in the ass, but we can optimize it using something that is called deltas. Just like when you are using Git, for example, when we are pushing our changes to the origin, to the remote branch, we are not sending the whole files that have changed. We instead are using diffs or only change sets of those files and publishing only those change sets instead. So we are doing the same here. When we are, for example, incrementing the state of our G counter for replica B, we first create a new state with updated value, but at the same time, we can create another G counter that is we treat as a delta, which is only a subset of the entire G counter that is consisting only of the entry that we have changed. And this way, we don't need to publish the entire state. All we need to do is to publish the change set itself. And this is just like that. Most of the deltas can be implemented using the same tools that the original CRDTs were using, and can be merged as well using the same merge operations that we are using on the full states. They have only one small downside, just as you remember on the timeline maybe not the timeline, on the diagram I've presented initially. The more we are moving through operation states, because this is a kind of operation, like we are sending updates instead of full states. We can treat them as operations. We need to enrich our replication protocol, because now we need to be sure that those updates were received on the other side. If we won't do that, then we will probably miss some of the entries that were lost during the synchronization process. If, for example, a remote machine that we want to replicate our delta to has died or something like that. So no, you cannot use UDP anymore using this solution. But probably none of us is doing that anyway, so it shouldn't be really a problem. The simple solution for that is that we send a delta, replicate data to other replicas during the standard update process. And from time to time, for example, like every minute, every hour, we are sending the full state to synchronize and correct the missing values. Because we are living in eventually consistent reality, remember? This was the topic of this talk. So yeah, we are in the appendix section. So things that I hoped I will have enough time to talk about, but wasn't sure. First is how to enforce consistency, because in theory we have eventually consistent systems. So this means that we have the writer can store updates on one node, for example, on one machine, while the reader is reading the same value from another machine, and he can get out-of-date values, right? So there is a way how to fix that. One of those ways is to do something that is called replicated write and replicated read. So when, for example, Alice is updating the state from x1 to x2, she doesn't have an acknowledgement, a response from our system right away, only after we have confirmed that the replication, that the replica was sent to majority of nodes in our system. So n divided by 2 plus 1. And only then we are sending the acknowledgement for it. Later on, when, for example, Bob is trying to read the value of the same value, he is doing a replicated read. So he also doesn't read only from one replica. Instead, he is choosing randomly majority of the replicas and getting back the states from them. Later on, before we send the states to the Bob, we are merging them together and updating the local state as well. And this way we can replicate as well. And this way we have this coverage that at least one of the nodes in our system will have the most up-to-date value. Of course, this is an issue because we are no longer able to simply work in the full offline mode, because we need to reach at least majority of the active replicas. But it's still a little bit better than using leader-follower replication, because we still don't need to waste time for the consensus. And coming back together again to optimizing our set, to remove tombstones and to reduce the size of those vector clocks. This is something that is called dotted version vectors. It's a great name. By the way, the name that is related to CRDTs quite often is called joint semilattice. My mind just kernel panicked when I heard about this first time, and I think that using names as such makes this whole topic a lot harder to learn than it really is, because as you have seen, all of those implementations fit into single sites. Sometimes I'm using font number 8 in size, but still they are fitting in. So yeah, going back to dotted version vectors. Here we won't be using a vector clocks per se, because what we have seen that when we are updating the value, we don't update the entire vector clock. We usually are updating the single entry. Just like with deltas, we can take the single entry. We are calling it usually a dot. That is marking the point in time, but not point in time in terms of physical time, but point in time in case of our vector clock. And it marks timestamps this single event, like insertion or removal, to a specific point in time in our logical time. Later on, we can join together all of those dots to build something that is called dotted version vector. And we can imagine it looks something like that. So since we are updating, sending those updates, sometimes out of order, we can have disjoint dots, those on the right side. But usually we are trying to catch all of the dots that happened in the past and join it to our seen version of state. So this clock, this blue mass that you can see on the left, will be progressing from left to right over the time, and eventually merging all of those disjoint dots all together over the course of time. And we can represent it very easily using two data structures. One is the vector clock that is describing this blue mass on the left, and it's describing it only by the edges of that mass. So, for example, D4 means that we have cached all of the events from 0 up to D4 for this value D, and for all of the other corresponding replicas. It's like building watermarks when we are building systems based on the timestamps. And we also have something that is called dot cloud, which is simply a set of dots that is having all of the disjoint dots on the right side. Usually this dot cloud is very small. So this is how our set looks previously. So we have two compound sets, one for added and removed elements. We had some entries inside, and each of those entries were timestamped using vector clocks. And this means that sometimes in some situations, our vector clocks, our metadata can be way heavier than the actual active result set that we are interested in. Right now, with this approach, we can represent it using something like that. So we can active set where we have our entries time-stamped only with the dots themselves that are representing the time in logical timeline when they happened, and something that is called either dot context or dotted version vector on the right, consisting of two data structures, that is describing the whole history that we have observed up to this moment in which this state is in. And as you can see, there is no longer a remove set. There is no longer tombstones. Simply because using dots, we are able to see when something has been removed or not. For example, we can see that there was a dot, some event of removal marked with value C3. We can see it in our dot cloud, but we don't see it in our active set. And that means that it must have been removed. Because simply, when we are adding elements to this kind of set, we are adding it to the active set, marking it as a dot, putting that dot into our dotted version vector, and that's all. When we are removing it, we simply remove it from our active set, and that's all. It has been already marked in our dotted version vector. So we already noted that it has been done. It has been there. We observed that removal. And when we are merging those two, well, we know how to merge vector clocks. Since dot cloud is basically a set, we know how to merge sets using union. And now when we want to merge active sets, we merge them just like the set, but in the process, we are removing all of the values that have dots that we already seen in the vector clocks on the other side, but we haven't seen the corresponding value in their active set. And that's all. So what's next? It turns out that this approach is not only limited to CRDTs representing simple operations. For example, you can, of course, have things like sets, counters, and so on. And for example, if you are using Redis, this enterprise version of Redis with CRDBs is leveraging the fact that their type system of Redis is actually using those simple types. But we can use it for building some entire documents that have JSON-like properties. And for example, this auto-merge library I was talking about, which you can use at any point in time you want, is basically a document store that you can update concurrently from multiple replicas, and those entire documents will be composed together into a single conflict-free document without any need for manual conflict resolutions. Another thing that you might be interested in are distributed transactions. One is called RAM, which is real atomic multiple partition or something like that, which is used, I think it is used in Amazon DynamoDB, because to be honest, I haven't found any information from them what algorithm do they use. But when reading the docs, it looked a little bit like the ramp transactions. I haven't talked about them here because we will not have enough time. And another one is Cure, which is used on this NTDB thing where you can do ACD transactions. I know I might speak not clearly, but there is a one letter missing in that because of CRDTs. There is no isolation between transactions because we don't need to isolate them because they will always converge to a single consistent state. And yeah, this is the summary. So in case if you are interested in going further, there are different talks, many different talks on this topic. If you are interested in building something by your own, I've created a series of blog posts. Sorry, I'm using an F# as a language of choice there, because this is my language of choice. And examples for those blog posts are also on my GitHub. If you are interested in building your own applications using for example, CosmosDB, there is a special link for the docs to building custom config resolution logic. And there is also a tutorial for using Redis Enterprise CRDBs if you are eager to use them. And the nice thing with Redis CRDBs is that they are not adding any extra, overhead, any extra keywords or instructions. You can use, if you know Redis, you can use those CRDBs in the same way that you were using Redis. Just read about, this config resolutions algorithm, so you will not reach into, some different states when you are adding and removing, for example, concurrently the same value from the sets from the two different replicas, and then the result was not what you have expected. So that's all, and thank you very much.